Yeah, ladies and gentlemen, I'm glad to start the board lecture, which we canceled because of COVID. And we are very grateful to our former alum, Casper Ernst, who contributed to this lecture series. And I'm very happy that we can do it again after 2 years. And Cliff will be in charge of this special talk for today and for tomorrow. Cliff.
Thank you, Yao. We're really happy to have Mike Freedman as our giving the Bott lectures today and tomorrow. Mike is the man when it comes to four-dimensional topology. So he proved the four-dimensional Poincare conjecture in the topological category and classified four manifolds with small fundamental groups. So that was kind of his opening chapter in his life, and then he moved into computer science and quantum computing. And so Mike was the head of Station Q at Microsoft and probably had a lot to do with Microsoft getting into quantum computing. So Mike is one of the two people, I think, who could possibly win the Fields Medal. Mike has won the Fields Medal, so he could possibly be one of the two who gets the Fields Medal and the Nobel Prize. So, Mike, we're rooting for you. So anyways, here's Mike Freedman.
Well, thank you so much for the introduction. Please, no one in the audience wait for that event. Life will move on way beyond it. So I had the pleasure of meeting Raoul in 1971 when I was a graduate student at Princeton. Bill Browder let me tag along to this conference in Mexico City, and Bott was giving a series of talks on Bott-style topology, classifying spaces and Lie groups. It was a beautiful series of talks. I visited Harvard in the fall of '88, and I was actually for a time in Bott's office because he was traveling, and rummaging through his desk looking for pencils, maybe some wonderful manuscript hidden away. I did find a manuscript, but it wasn't math. It was a lecture he had given on his 25th anniversary of being a Harvard professor. Apparently they asked a professor with that tenure to speak to the undergraduates at graduation. And it was stunning to read through this. The first thing I noticed it was that he had a better command of the English language than I had, which, since he's native speaking Hungarian, I found impressive. His lecture was read like stand-up. Just to give you a little flavor of Bott, he was very proud of the fact, he's proud of his ability to drink, and more than that, the fact that the Russians that he knew, the Russian mathematicians, respected him in that category. But in those days, in the late 80s, I don't know, there was some concern that drinking was bad for your brain. And one of the things Raoul computed in that lecture was the number of brain cells he had lost in his 25 years at Harvard, partially due to drinking in his estimation. But then he rejoined it. He said, well, maybe it's not the brain cells that are important, but it's the space in between them that's important for the ideas to emerge. So all the better. So in that spirit, let me launch in. So these talks will be on the interface of math and physics, and I'll try to make it clear which is which when I'm talking. This talk is more oriented toward physics with a lot of numerical work and computation. I would introduce my co-author on these papers, Modj Shokrian Zini, who I hope is listening in. And the titles of our papers on the arXiv are Universe from a Single Particle 1 and 2. And what this refers to is a kind of symmetry breaking, which I'll explain. between single particle quantum mechanics. So you start sort of with first year undergraduate quantum mechanics, and after a symmetry breaking, spontaneous symmetry breaking, you end up in more familiar interacting physics. So a good place to begin is with this idea of spontaneous symmetry breaking. And there are famous examples that you all know of. There's, if you take red hot iron and you slowly cool it, when you cross a temperature that's roughly 1,000 degrees Kelvin, the rotational symmetry of the magnetic moments of the iron atoms is broken. It's no longer fully rotational, and a lattice forms, and what you get is a magnet. Another example is Ginsburg-Landau theory. At a phase transition, you get a superconductor, or at high energy, famous maybe from the discovery 5 years or so ago, the Higgs, there's a symmetry breaking which produces mass. So the only purpose of this list is, if you're a mathematician, to think that spontaneous symmetry breaking is a very general phenomenon in which the solution or the ground state has less symmetry than the physics that it's minimizing. So it has less symmetry than the Hamiltonian. That's the origin of the term breaking. It breaks off into a lower group. And these examples of symmetry breaking and all the classical ones are at the ground state level. The ground state is less symmetrical than the Hamiltonian. But I'm going to be talking today about symmetry breaking at the operator level. So that'll be a little bit different. And it'll actually be technically on metrics on the operators, in the space of metrics on Hamiltonians. The metrics on the space of Hamiltonians will be the kind of venue for this symmetry breaking. So I'll really spend the beginning part of the talk just explaining what this novel symmetry breaking is and how we can think of it as going from sort of an undifferentiated single particle Hilbert space to interacting physics. So a good place to begin is with the what's called the GUE, which is the Gaussian unitary ensemble. And it's the most standard probability distribution on Hamiltonians introduced by Wigner in 1956. And what it says is that the probability of seeing some Hamiltonian is proportional to e to the minus the L2 norm of the Hamiltonian squared, which is the same as the exponent here is the same as trace squared. And if you go from Hermitian to anti-Hermitian, if you put in an I in the right place, then this is familiar as the, either of these is familiar as the killing on SUN. In other words, we think of these as in the Lie algebra of the unitary group as skew Hermitian matrices, then this is the Gaussian, which is round with respect to the ad invariant metric on that Lie group. But what I want to point out is that what's regarded as a random Hamiltonian depends on this inner product, whether it's the L2 inner product or some other inner product. And you might have some different metric rather than the L2 metric on Hermitian matrices of some size. So you might have some other metric, which I'll just call Gij, instead of this L2 metric. And then that would lead to another Gaussian. You might write G sub Gij, which would just be proportional now to e to the minus Gij HIHJ. So in other words, with a different metric on the linear space of possible Hamiltonians, you'll get a different probability distribution on them. And one drawn from such a probability distribution might look quite different in terms of the physics it would represent than one drawn from the GUE. So let me give an example of another probability of another metric that you might draw. It's kind of an important example. So this example is actually taken from a topic that's currently of a lot of interest in the theory of black holes, early universe work. So this is example is called the penalty metric. It was introduced a few years ago in papers by Brown, Adam Brown, and Lenny Susskind. So to explain this, let's just think about the Hermitian. I'll just be very concrete, the Hermitian 2x2 matrices. So this is the span of the identity X, Y, and Z. These are the Pauli matrices, where X is this 2x2 matrix, sometimes called knot. Y, this Hermitian matrix, and Z, this one. So this is the basis of the 2x2 Hermitian matrices, and these is the Pauli basis. And if we want to look at the Hermitian matrices in a higher dimension, say the Hermitian matrices in dimension 2 to the n, it's convenient to note that this is equal a tensor product of qubit factors. So Hermitian 2x2 matrices, if we tensor up n copies of these, we'll get the Hermitian matrices to the n dimensions. And this leads to a natural basis that this is the span not now of the Pauli matrices, but the span of the Pauli words. And a Pauli word is just some string of letters and ones tensored together. Like here's an example. And this is for n equal 1, 2, 3, 4, 5, 6, 7. And we would call the weight of this Pauli word 3. This example, because it has 3 non-1 letters. And now the example I wanted to say, the penalty metric says the Gij is going to be diagonal in the Pauli word basis. It's a diagonal metric. So it's delta Ij times some base, and I'll just say E, so it doesn't have to be E, to the weight of the ith word. So in other words, what this does is it says it penalizes words of large weight. Well, words of large weight are not many body interactions, like the Heisenberg interaction is two body interaction. It's built up of terms XX, YY, ZZ, twofold tensor products. And what this metric does is we think of the Hermitian matrices. And by the way, I'm using the language Hermitian matrices, but in the back of your head, you should sometimes add this I in front and think of them also as the skew Hermitian matrices. So they're the things you exponentiate to get unitary evolution. So what this metric does is it says that words with high weight, the distance to that word is very long. So it's expensive in the Lie algebra to move in that direction, but low weight words, you can move easily in that direction. So if you select a metric, if this is your metric, and using this metric, you constructed a Gaussian ensemble, it would look quite different because the typical vector that you selected using this inner product would represent low body interaction rather than the generic n by 2 to the n by 2 to the n matrix. So with this example, now there are sort of two examples to think about: the add invariant, completely symmetrical GUE, or something that favors interacting, what we think of as interacting physics, namely most of the weight of a random Hamiltonian with respect to this metric would be consisting of 1, 2, maybe 3 body interactions and very rapid exponential decay for higher interactions. So with these two examples, let me make a definition.
Hey, Mike,
Yes,
can I ask a question?
yes, please.
Are you allowed to have a Hamiltonian like 1 plus epsilon z? I mean, is it really the span of those, or is it really, or just a word in those?
One.
So suppose I had a Hamiltonian.
Yeah, I took the linear span of the Pauli words, what I'm calling the Pauli words, are a linear basis for the Hermitian matrices in exponentially many dimensions. So, and conveniently, the metric I'm describing is diagonal on that basis. So the way I describe the metric is I just said, it's difficult to move in the directions that have a high body interaction, and it's easy to move in the directions of low body interaction. And actually, Mike Nielsen studied this metric in 2005, and also with collaborators, as a kind of continuum model for quantum compiling. In other words, if you're trying to get somewhere in the unitary group, like somewhere might be Shor's algorithm, then you might ask, well, what's the fastest way to get there? What's the fastest way to produce that unitary that is Shor's algorithm? And well, you get quite a different answer if you didn't have the restriction that the steps you take to get there should be in low body directions. They should follow the gates of a quantum computer, basically. So this metric can be thought of from a computing perspective as referencing what's capable, what's easy and what's not easy to do on a quantum computer. You know, short will be what's easy to do on a quantum computer. And, but it also curiously is interesting from a study of black hole physics, because it models how the degrees of freedom on the event horizon should be interacting with each other in order to get good agreement with some of the expected time scales.
Thank you.
So, yeah, so let me make a small series of definitions. So these are the only definitions in the talk. We'll say that if you have an isomorphism, which I'll call capital J, from small Hilbert spaces, say qubits tensored up n times, you see 2 to the n. Choosing this isomorphism J is what I'll call a qubit structure. And it can also be expressed in terms of an induced map, which I'll write lower j, which is the isomorphism between the Hermitian 2x2 matrices, again tensored up n times, to the Hermitian matrices in the larger dimension. This is lower j, and this j induces this j. Now, given this definition of qubit structure, I'll say that a metric, this is perhaps the key definition I'm writing now, a metric Gij, as before, on Hamiltonians, this is a metric on Hamiltonians, knows about qubits. So that's this abbreviation CAC, knows about qubits. If Gij has a basis of principal axes, I'll call them, so it would be k of them, h sub k, where k goes between 1 and 4 to the n minus 1. So this is the dimension of the Hermitian matrices. That's this index. It has the basis of these, which have a tensor product form. So as a basis, actually, let me put the quantification here. It knows about qubits if there exists a j as above. There exists a j as above, such that this has a basis, the principal axes with hk equaling j Okay, so this it's important to absorb this definition and what it means. So let me just go over it again. So let me go over it in pictures, actually. So we really have two metrics in mind here. One is the L2 metric, or the killing metric, the symmetrical one. And then the other is this arbitrary metric, Gij. If you have a reference metric, which in this case is the L2 metric, and you have a second metric, then the second metric looks like an ellipsoid with reference to the first metric. And you can talk about its principal axes. You could also equivalently talk about its eigenvalues if you use the first metric to raise an index. So what does this knows about qubits definition mean? It means that the principal axes, which are sort of the canonical directions for this ellipsoid, these are directions in this Hermitian matrices of size 2 to the n. It says that these directions are actually tensor directions. They're not just kind of random directions. See, all directions here are linear combinations of tensor directions. But it's a very rare direction that's tensor on the nose. And for instance, if we had SU4, the smallest case we consider, there generically will be 15 principal axes. So it's a very strong condition to say that for one fixed qubit structure, J, all 15 of these axes will be pointing in exactly tensor directions. So maybe I should pause to answer a question if there is one about what the meaning of this, what the definition is or what its interpretation is. Or perhaps I should just go ahead and we'll see how this is used. But what you should have in mind is it's a very rare, if you count dimensions, the fraction of dimensions as n goes to infinity, it goes to 0, the fraction that are CAC. In fact, in dimension n, roughly square root of, if the dimension of the Hermitian matrices is n, roughly square root of n up to log corrections is CAC. So it's a quite a stringent condition. Well, what does symmetry breaking require? Symmetry breaking requires a functional. So in our context, what this functional will be, we'll call it delta, and it'll be a functional from the metrics. I'll normalize the determinant one metrics, well, metrics on, let's say, Hermitian n by 2 to the n by 2 to the n matrices, going to the reals. And the reason I call it delta is I want you to think of it as sort of a pseudo energy. So I want you to think that the probability of producing a metric is maybe proportional to e to the minus delta over some KT, where this is some pseudo temperature and some pseudo energy. So that's sort of why I'm calling the functional metrics delta. And the general pattern that we'll have is we'll define these functionals. I'll give some examples in just a moment. And very often what we'll find is that the killing metric, or this L2 metric, is a local maximum for these functionals. And there's some minima, local minima. And numerically, we search out these minima. And very often, order 1% of the time, like 30% of the time, 50% of the time, we find these are CAC. So this rare linear algebra condition, it's rare from a dimension counting point of view, turns out to be common in the local minima that we find, at least for certain classes of functionals. So the interpretation is that if there's some process which imposes an energy on the choice of the geometry, yeah, maybe I should explain the logic this way. So the logic will be, we'll pick a delta, pick a functional, and then we'll find a minimum, a local minimum metric. Once we find the local minimum metric, we'll produce the Gaussian. And once we produce the Gaussian on Hamiltonians, then we'll pick, using that probability distribution, the Gaussian probability distribution, then we'll pick a particular Hamiltonian. So I'll call this the Hamiltonian or universe. And the idea is that we start with a situation in which there's no spatial structure, there's no even tensor product structure into local degrees of freedom. in our states, or states are look maybe like a simple harmonic oscillator, just states of a single particle, maybe not infinitely many, but a large finite number of states. And then if we break symmetry with a functional to find a local minimum, and then use that local minimum to draw a random Hamiltonian, we'll find something that this Hamiltonian is interacting. Interacting is equivalent basically to up here, this Gij should know about qubits. So it means that a random Hamiltonian built from this probability distribution or pulled from this probability distribution will look like small body interaction. So to make this more concrete, let me give you the basic example to think of this functional delta. So the basic example is the Ricci scalar. So one can compute that in this case, the Ricci scalar is given by this expression. So what does this diagram mean? Well, there are really only two tensors in the game. And there's the metric, Gij and its inverse. And there's the structure constants, Cijk, of the Lie algebra. These are the structure constants of SU2 to the n. So that's what I've drawn here, is I've drawn sort of in Feynman notation, if you like, what the Ricci scalar curvature is. It's some closed up linear combination of closed diagrams, so it's a scalar. And the trivial vertices are the structure constants of the Lie algebra, of the Hilbert space symmetries, and the arcs are the inverse metrics like this and the metrics like this. So for example, this diagram is Cijk, Cijk with primes, and then 3 Gs, Kk prime, I prime, J prime. That's right. And this diagram is Cijk, C, this is G, I prime, and this K goes to a J. This J goes to a K. So just to recap where we are, this is something we would study as a functional on metrics. Now I've used two different languages, so let me try to clarify this. I've talked about metrics on the space of Hermitian matrices, but probably geometrically what's better is to translate that in your mind by inserting the I and thinking of it as a metric on skew Hermitian matrices, which would be the Lie algebra of SUN. And then when you give a metric on that, on the Lie algebra, then there's a left invariant metric defined on the entire Lie group. And it's the Ricci scalar curvature of that metric that's computed from these tensors in this way. So So the investigation, now I'm going to move to data slides. The investigation is to consider families of functionals of which Ricci scalar curvature is one, numerically seek out left invariant metrics on the Lie group, if you like, at these minima, and study them to see if they know about qubits. And the amazing thing is, it's actually rather common to find metrics that know about qubits. And therefore, we propose that this kind of symmetry breaking is a natural way for the Hilbert space to gain structure. You start with sort of a naked Hilbert space that's not a tensor product, and it becomes one. So I'm going to share my screen now, see if this works. Can you raise your hand, Cliff, or wave if you can see my screen?
Yeah, I can.
Okay, great. Okay, so this slide just describes a class of functionals that we studied numerically. And what they are is they're perturbed Gaussians. If you look at it, what we did is we just tried to do the simplest possible thing. After all, as I explained, the only two things we have lying in our hands to build functionals on these metrics is the metric itself, which are the arcs, and these three tensors, the structure constants. So, you know, morally, the arcs look like quadratic terms and the vertices look like cubic terms. So we just build a perturbed Gaussian, and this is the simplest one that you can write down that doesn't, where the cubic perturbation doesn't vanish on symmetry grounds. You know, the two lower indices of the structure constants are anti-symmetric. So you have to fiddle around to find Gaussians that do this. But this has the advantage that there's an expansion parameter in these functionals, K, which is very useful in finding local minima. In the first example I gave, Ricci scalar, there is no parameter, there's just one functional. So numerically, it was very useful to have a parameter to search, to vary in the search. I'm having trouble advancing the slides. Let's see. Oh, there we go. Okay. So this slide summarizes what we found in the case of the Lie algebra SU4. By the way, the Lie algebras that I'm going to discuss, where we did numerics, go from SU4 to SU8. And SU8, if it breaks into qubits, that's just 3 qubits. And you might wonder, why didn't we do numerics with 30 qubits or something like that? You read about simulating quantum computers. But there's a fourth power that comes here, because if we're talking about a Lie group SUN, then its Lie algebra has dimension order n squared, and metrics on that have order n to the fourth. So it's numerically already in SU8, we're already searching a 2000 dimensional space of metrics when we want to know where a functional is minimized. So, but anyway, here's the start at SU4. And, you know, we found tens of local minima, particularly by varying that expansion parameter K. And we used 2 different versions of that functional. These are nicknames, 2.6 and 2.4. 2.6 is the imaginary part of the functional I had for you on the board, and 2.4 is sort of a real version, a Wick rotated version. And the nickname has to do with how many diagrams we kept in the expansion. 6 means a 6 vertex diagram. Those diagrams were kept. The CAC ovals knows about qubits. The sub-labeled ovals are sort of distractors that we had to be careful of, because we found when we started doing numerical experiments that sometimes Lie algebras were picked out, sub-Lie algebras, rather than something to do with qubit structures. And it turns out in low dimensions, these overlap a bit. So for example, SU4 has a sub-Lie algebra SP2 and also SO4. And we found with scalar curvature, we found minima, which could both be explained as sub-Lie algebras, which in both cases were known analytically. But also it turns out the generators for these sub-Lie algebras are have tensor product structures. So they can also be classified as CAC. But as we proceeded and tried additional functionals, very quickly we found new minima, which were not new CAC minima, which were not related to any sub-Lie algebras. And then just to explain my footnotes, slightly delicate, that means that this minima appeared and disappeared as we varied the expansion parameter. And terminology of the penalty terminology, the SO4 metric is one of the Susskind penalty metrics. This is the slide for SU8. Again, I skipped the numbers between 4 and 8 because I was focused here at powers of 2 and asking whether they would decompose into qubit structures. And again, we find a number of instances. And I should say, oh, and for both slides, let me say what these long strings of numbers are. So the Lie algebra of SU8 is 63 dimensional. And if you look at one of these rows of numbers, any of those rows of numbers add up to 63. And what these are doing is listing the principal values in degenerate clumps. We find that we don't get 63 independent principal values, but like we get 10, a group of 10 that's all the same value that forms a linear space, then a group of 15, then 1, then 32, then 5, in that example. So these numbers are listed according to size, so the smallest principal values to the largest principal values. And in one of these decompositions, it doesn't decompose all the way to 2 tensor 2 tensor 2, but to 4 tensor 2. That's noted at the bottom. So, and then what I should say is we have very nice numerical quantitative measurement of how accurately CAC is seen, because the definition I put on the board for CAC is that there's a basis of principal vectors which are exactly tensor products. And of course, nothing will be exact, there'll be some round off error. But the astonishing thing is we're almost never left wondering. When we look at entropy measures, which show you how much one of these principal vectors fails to be a tensor product. When we look at those entropy measures, if it's trying to be a tensor product, these answers are like 10 to the minus 3. And if it's not trying to be a product, they're order 1. So we see very little in between 10 to the minus 3 and 1 when we numerically try to assess how well something is found a tensor decomposition. So it looks like there's really a strong attractor to these tensor product structures. Now, a second paper, which is on the arXiv just a week or 2 ago, we decided to look carefully at the numbers that were not powers of 2 just to see what would happen. And we found quite an interesting thing. We found that if you throw in the situation where it could not possibly decompose as a tensor product, like a prime number, so the Hilbert space is dimension 5 or 7. Well, maybe I should say first what happens for 6. For 6, we find situations where the decomposition is just a qubit and a qubit. So that's perfectly expected. If qubits are showing up for powers of 2, why not qubits and qubits for 6? And in fact, it leads you to speculate that maybe if you put in an enormous number, it's the statistics of the primes and its factorization would become important. But the second thing we found is that maybe that statistics is not so important because it seems that when nature is searching for these local minima, it's willing to round off. So we found these things we call Almostcac, which are basically when the Hilbert space just throws away an inconvenient dimension. So C5 discovers a tensor decomposition for 4 of its dimensions, and then an additional linear space, and similarly for C7. And if you think of the factorizing block as the upper left block, then what we see there is those blocks, again, to high numerical precision, decompose as tensor products. But then there's sort of a repertoire of states that are left out, that are not part of this interacting physics world. And we refer to this as the leaky universe possibility, that maybe our leaky universe has some small number, like log the dimension, of degrees of freedom that just never got collected into interacting physics. And I tend to think of this scenario as potentially hazardous to our health, because overlap of our wave function, significant overlap with these unformed states that are not participating in our usual physics, does not seem like it could be salubrious. Sorry. So yeah, these are some details on the Almostcac pattern. Again, the exact dimensions and what we see with the subs and the non-sub patterns. And this is the similar information for 6, factoring as qubit and a 3 qubit and a qubit. This talk about dimensions, about bases. The numerics is sensitive sometimes to which basis we initialize the computation in. Let's see, this is, and these are the results for SU7. Then the last thing we did, numerics on, we went back to the powers of 2, so 4 and 8, and we considered a different possibility. We considered the possibility that the local minima would not be novel because they knew about qubits, but maybe they knew about Majoranas. So Majorana degrees of freedom are, are like square root of 2-dimensional. You need 2n Majorana operators to express all the Hermitian matrices of dimension 2 to the n. So you can ask for the principal directions now not to be tensor product, but to be homogeneous polynomials in Majoranas of some particular degree. So this work is not completed, it's still in progress, but we do find, we do so far have the following results for knows about Majoranas. And again, we investigated the same functionals. And for SU4, we find this structure with various degeneracy patterns for both functionals. SU8, we're still playing with the computations, and we found patterns which have the Majorana structure, but only for about 55 of the 63 vectors, the 63 principal vectors. So this is a little bit uncertain. I should mention, maybe I'll just click back to the very first, well, actually, yeah, let me try getting back to the very first slide, one of the first slides. Oh, yes. I forgot to call attention to this, but if you look at the bottom oval, there's a pattern which you'll recognize as Pascal's triangle with the 1 cutoff, 1, 4, 6, 4, 1. So that's the degeneracy pattern we saw early on in SU4, which we realized when we did the Majorana study is the Majorana physics raising its head. So 4 means that these are the 1 Majorana operators, the homogeneous of degree 1 in gamma 1 through gamma 4. The 6 represents the 6 quadratics in 4 Majorana operators like gamma 1, gamma 3, et cetera, and so on. So these produced self-contained principal directions. So my final slide, so the overall conclusions are, I would say that nature abhors a naked Hilbert space. It would like, if given the opportunity, to dress it in some additional structures, tensor or possibly Majoranas. A random initial dimension for the universe is something that is very interesting to think about. Actually, I had a nice email conversation with Noam Elkes at Harvard about the statistics of approximating numbers by what are called smooth numbers. So a very easy example of the first example of smooth numbers would be things that can be, whose prime factorization only contains 2s and 3s. It turns out that even allowing just 2 primes like that, you can get very close to any number. It's if you ask how much do you have to round down a number for its factorization to be 2s and 3s, turns out it's only about log of the amount of the number. So this is my remark about the leaky universe. If it's important to break into small degrees of freedom, then there might be like a log-sized piece of the universe left out, the leaky universe scenario. And maybe the next thing we're going to look at is follow up on a suggestion of Adam Brown, who said basically that, well, you shouldn't just investigate an initial Hamiltonian. What's important about the universe is a pair. It's the initial Hamiltonian, comma, the initial state. And if we just add a source term of suitable projector to encode an initial state into the functional, the perturbed Gaussian functionals that defined our functionals, if we add that source term, then we can not only minimize the metric, but we can minimize the functional now as a function of metric and source. So we can look at the two together, and then will enable us to study things like the production of entropy under the Schrodinger equation. So we can see if that looks at all like our universe. And a final suggestion, which was made to us by Greg Moore, is, well, we've kind of pointed out how degrees of freedom might arise, how locality could arise. That's the tensor product structure. But we haven't yet said anything about how space arises. And space means the local degrees of freedom are not in the complete graph. They're not talking all to all, like in maybe some black hole models, but they're organized spatially. And it would be interesting to try to have some insider speculation, at least, as to how space can emerge from this kind of symmetry breaking. And in particular, the suggestion was that the Leech lattice should be a good target as the sort of generic bit of space related to string theory. So maybe that's a good place for me to pause, and I'll be very happy to take questions.
Thank you, Mike. So there is a question already. Sean Quee says, hi, Mike, if the ambient space has dimension of power of a prime other than 2, say 3 to the n, will your algorithm tend to find qubit factors rather than qubit factors, or is this not relevant?
It is relevant, and we strongly expect that if we studied dimension 9, we'd find 3 tensor 3. We haven't done 9 because of some numerical instability, and we may still yet attempt it. But as I pointed out, the dimensions for the Serge grows as the 4th degree of the dimension of the Hilbert space. So going from 8 to 9 actually more than doubles the effort. But I think that's what we expect to happen, yes.
Other questions? Hey, Mike, I have a question. So, our universe, at least locally, has a sort of, the Poincare group, or SL2C. I mean, can you sort of build that in somewhere? Like, assume.
Well, I don't want to build it in until I've found space. That is, I mean, this Poincare group has to do with spatial space-time symmetry.
Well, no, but I'm suggesting if you have, qubits, then you have SL2C. I mean, you're weighting it to see SL2C basically. So one would expect space to come out as a representation of, of SL2C. I mean, in some ways you're weighting it by qubits. There is a natural SL2C action, right?
Yeah, so I actually, this relates a little bit to Sean Sui's question, which is what about 3 instead of 2? So though I spoke most of the time about qubits because that's kind of a natural and familiar language, I'm really not expecting that qubits are very much more favorable than qtrits. If you just took a large integer and tried this with a much more powerful computer than we have or could ever have, I'm guessing that 2 would not be particularly singled out, that it would break into products of small primes for the tensor decompositions. That's just a guess. But so does that impact your suggestion if it's not qubits, if it's
Yeah. Other questions? Well, thank you, Mike. It's a lot of food for thought here. So
thank you guys.
So tomorrow at 11, we meet again, and you want to say something about tomorrow's topic?
Yeah, so tomorrow's topic is, it's maybe philosophically connected, but it's completely disjoint mathematically, and it's a more mathematical discussion. So for tomorrow, we're going to start with the idea that gauge theory is an interesting thing. And so that's like much more advanced understanding of the universe, that we have space and fields and so on. And then the question is, the question I want to discuss is, to what extent can curvature be replaced with flat connections? So the prototypical example of this is this Miller-Wood discussion, where they show that circle bundles over surfaces up through a certain range of Euler classes can be written as flat PSL 2R bundles. So in other words, instead of trying to write a circle bundle as a U1 principal bundle, you could try to write it as an SL2R associated bundle, where the SL2R is acting by isometries of hyperbolic space and therefore acting on the circle at infinity. And it turns out that when you enlarge the structure group, more bundles become flattable. You can make them flat. And I'll be talking about this in the context of what's called Mather-Thurston, which is very general discussion about bundles with fiber manifold over a manifold when you can produce a flat connection.
Okay, great. Thank you, everybody. Hope to see you all tomorrow then. Thank you, Mike.
Terrific. Okay. Well, I'm looking forward.
Thank you, Mike. That's good talk.
Well, thank you, Al. Nice to see you.
Yeah, tomorrow.
Okay. See you guys tomorrow. Bye-bye.